from this left to this right side. Okay, so that's the flow directions. So when the water is going from left to the right, and the other thing I should mention is, let's say this is a smooth pipe maybe. So smooth pipe means zero roughness. Here, if we say this is the cross section, so that means this is the wall, the top wall and the bottom wall. It is a smooth pipe. Roughness is 0. What we can expect that the flow will go, a steady way, like it will be more smooth flow. There will be not that much, the pressure variations. If we say this is the inlet point 1, this is the point 2, so we can say that the flow, overall flow, it will be so smooth. There will be, no loss. Okay, but when we will insert a so you can correlate it from here. So this is a pipe, and now if we insert a valve, why we will insert a valve here? What's the intention? The main reason is we want to restrict the flow rate. So we usually use the valve in the piping networks. This is the only target, is we really want to restrict the flow rate. We want to increase or decrease the flow rates. So when it will happen, this is kind of it acts like a fin, some sort of resistance. Flow cannot just pass it, but it flow needs to deviate due to this obstruction here. So what usually happen when we insert this sort of valve, we can see some loss here. Basically, you can simply say, for this pipe, this is the surface area, or you can say this area from here to here, this is the fluid flow surface area. But when we inserted this pipe, this valve here, then you will see it reduces like this. So the surface area, the fluid flow surface area reduces. That means it becomes narrow. Now it is acting like a the stenosis pipe. So it's kind of the contractions. And what will happen due to this contraction, this narrow surface area will expect high velocity here and the low pressure. So we will experience some sort of pressure, some loss, and this loss we usually call this the minor loss. So in piping system, we not only use the valve, but we use all these components. When you're talking about a piping system like here, you will see a lot of things kind of this bends, valves, joining. Sometimes not everywhere in the piping system the diameter is constant, but the pipe diameter, it varies. So sometimes it expands, sometimes the diameter reduces, like the contractions, and the different shapes of the inlet and the outlets. We use the elbow fitting, all these things that eventually give us some sort of minor loss. So when we will think about a piping system, we will get a lot of this, and what we'll get the minor loss. So previously we know how to calculate the major loss, and now we said we're going to talk about the minor loss. So what actually happened? This minor loss, this is very small. That's why it says sometimes it is negligible. Let's say you have a long piping network. So if you have some bends or some fittings or elbows, then we can say this minor loss is negligible. But my conclusion is, now I will show you two things. We have one pipe where we have the friction loss, and this is one pipe, let's say we have kind of a stenosis section like this. So for this case, for this pipe, we have the major loss. Here we have minor loss. So I'm just talking when we have all this thing. That means this fittings, valves, or any of this arrangement or inserts. This minor loss, in some cases, it could be significant than the major loss. Is it possible? We said the friction loss is the major loss, and all this reason, it is the basic causes of the minor loss. So what I said is minor loss, it could be significant, or it could be higher than the major loss. Is it possible? So when we said minor, that means this is kind of negligible loss, and the major loss, the friction loss, it is major, it's significant. So is it possible that the minor loss, it will be significant, or it will be significantly higher than the major loss? What do you think, guys? Just yes or no. So it is very clear that major loss, it is significant. Yes, so some of you said no, but it could be. The minor loss, it could be significant. It could be higher than major loss in some cases. When you have a large, or long piping system, then the minor loss is negligible. But if you have a couple of this insert in very short distance, let's say you have, this is the valve. Now you have another valve here. So we can say this valve is from this way. So this is another valve. You have one more valve here. So if you have a multiple this component at very close distance, then this minor loss, it could be higher or significant than the major loss. What actually happened? I will just draw one more pipe here. Let's say this is a stenosis pipe. Okay, and this is quite long. So the flow is going through this. Basically, the flow will be significant, the fluid velocity will be significant here. Once the fluid flow will pass this narrow section, it will gradually, so if the flow is fully developed here, you will see it will become kind of this again when it is a long pipe. So there will be some gradual transition of the flow. If you have just one narrow sections, this kind of contraction, the pipe. But if you have a multiple like this in short distance, then flow will not get enough surface space. And in that case, there will be some loss, there will be more loss, there will be more loss. In that way, when it will just, you have more than one this sort of component in your system in very close distance, in that case, the minor loss could be significant than the major loss. So this is the theory. And now how then we can analyze all this loss? In real case, it is really hard to calculate this minor loss if you want to do it manually. So suppose you are using some fittings in your piping system from different manufacturer. So they have different product, and if you will see, so let's say I'm one manufacturer and you are one manufacturer, we're producing same fittings. It looks identical, but the loss coefficient, it will be different. It could be different, slightly different for different manufacturers. So we actually need to follow their handout, and also we need to just compare it with the existing setup or some of their measurements. So what actually happened, I said it is complex to calculate the loss coefficient. Then how we will do that? So this actually makes our life easier. So basically, there are some established values, some benchmark experimental data for all these different types of components. And we usually analyze this loss, the minor loss, by using the loss coefficient. This is called KL. And we say this KL is equal to Hassel over B squared 2G. This Hassel, you already know, this is the head loss. This head loss, it is the additional head loss. Let's say we put this valve. So due to this valve, we will have some head loss. This Hassel is the head loss due to this insert, due to this insert of the valve. So what you can do, you can just increase or decrease this section by using this valve. If you want to completely block the flow, then you can do it. If you say, okay, now I will just make it like 50% block or 75% block, you can just control it from here. So for different arrangement, you will have different head loss. And this Hassel, this is this irreversible head loss due to this block. And we know the Hassel equal delta PL over rho G from previous class, like how to calculate the head loss. So I will show you some equations and some charts where we will directly get this loss coefficient for different arrangement, for bends or the inlets, the exits. You will see there are a lot of different arrangements. So, and that's why it is really important when you will deal with a real project, you must need to check it carefully. And that we will try to understand. Maybe, the first 45 minutes or 50 minutes, we'll discuss theoretical things, and then we'll start with the technical problems. The technical problems are quite easy. So we said this is the the loss coefficient formula. KL, this is the loss coefficient. This is the head loss, Hassel, and V is the velocity, G is the gravity. All of you know this. How? And then Hassel is delta PL and rho G. Look, the question is how you can calculate this delta PL. This is actually the pressure loss. We have two systems here. This is without any insert, without valve. This is with valve. Same velocity, same flow rate, same diameter. Everything is same. This setup, everything same. We said this is inlet 0.1, outlet 0.2. So at inlet, the pressure will say P1. At outlet, we'll say pressure P2. The same thing when it is with the valve. So what will be the pressure variations between this 0.1 and 0.2? So we can say this is P1 minus P2, and this is also P1 minus P2. So that means the pressure variations between 0.1 to 2, how the pressure drop is happening. When we will calculate this Hassel head loss, so when it's delta PS, this delta PL, this is actually, it is kind of, if I say, what is the pressure variations between when you use this valve and when you had no valve. So it is actually you look here, it is the pressure variations when you inserted the valve minus without the valve, and this variation, this is called the delta PL. If you don't know it, it should be fine, but for some problem you need to use this formula. So we're going to solve two problems where you may maybe you do not need this, but what I said, you just keep in mind this loss coefficient KL equal Hassel this and Hassel equal this. So what we learned from this slide is all this component, it could lead to some sort of minor loss, and minor loss, it could be significant than the major loss. And we can calculate the pressure drop between a system when we inserted the valve, and so with valve and without valve. So if it is the arrangement, then what will be the pressure loss? So this is what we learned from this slide. So now I'll tell you just one thing from this slide. You can also correlate this minor loss with the length of the pipe. So here we can see one expression, and this expression says this is the length. So we have a pipe, this is the length. What is KL? Loss coefficient, the minor loss coefficient. What is F? F is the friction factor, D is the diameter. What we can see that this loss coefficient, it also depends on the length of the pipe. We understand from previously, okay, all this highlighted arrangement or insert, it is the reason for minor loss. But from this expression, what we can say, this is proportional. You see, L equal D over F into KL. So we can say this loss coefficient, it also depends on the length of the pipe. And here, if you are confused, like why KL equal delta PL rho V square, you need to just substitute this Hazel value here, and then you will get it. And if you further simplify this, then you may get this as well. So forget about that. We are going to use these expressions for the loss coefficient in some cases, and for most of the cases it will be given in the problem. So I can see some in the chat. Is the okay? No, not that. So okay, so what I said, I will not actually spend more time with this slide, but what I said, the loss coefficient, it is also equivalent, it is proportional to the equivalent length of the system. There are a lot of things I can discuss, but maybe you may lose your interest. So what I will do, I will not go, that deep from different angle, but I will just try to provide you the sufficient knowledge about this. Okay, here, this slide is very important. We already spent 20 minutes, more than 20 minutes, but you must need to understand this slide, guys. As an engineer, you must need to understand it. And this is, you can say, like 20% of today's lecture, if you can understand this. We have two things. So we said earlier, the total and the head loss, this is major and the minor loss. Okay, so this is major loss, this is minor loss, we know. And we already used this expression for some of our previous problems. And for the minor loss, we said, okay, this is the expression for the minor loss. Look, this is KL, the loss coefficient, B squared 2G. Why is the summation? In a piping system, we could have bend, maybe multiple bends, multiple valves, the inlet, the outlet, all are related with the minor loss. So we need to sum all those minor losses. We have got the second problem where I will show you how to do this. Now, this is the total head loss, and it is very, I believe it is crystal clear to you that, okay, this is quite easier thing. Now, look at this two figure. Can you see any difference between these two figure, guys? You see, this is the inlet, the pipe inlet, and this is the pipe. The same diameter, this D and this diameter here, it is same. This line here and this diameter is same. We can see this is the center line, this is the center line. Look, the streamline, the fluid streamline, it looks quite similar. It's almost same, but what we can see for this case, the loss coefficient is, it's nearly 0.03 and it is 0.5. It's kind of, how many times? It's significantly higher. The only variation, only difference between these two systems is we can see in this case, it is a sharp 90-degree angle. And here, you look at this section, this is kind of a well-rounded shape. Well-rounded shape. And you can see that's the only difference. And this is a small difference. Even it is not inside the pipe, it is the inlet where the fluid is just going inside the pipe. So this inlet section is really important. If you want, you can take notes. The minor loss at the inlet section depends on the shape of the inlets, but it doesn't, make that much difference when we have different outlets. That I will prove and I will show you, I'll discuss you later. So let's say this is the inlet. Inlet means how the flow is entering into the pipe. Outlet means, it's going out. So here what is happening, when it is the rounded shape, the well-rounded shape, fluid particles, we have one fluid particle, let's say here. This fluid particle, when it comes through this way, so I will put some arrow, that means this is the directions, like how this fluid particles are going. The same thing here, the same thing here. This is the vector sign. Now, what is happening? When this fluid particle is coming here, due to this this smooth change of the curvature, it can, smoothly just make it turn like this, and it can go this way. But when you are using a 90-degree shape, that means a sharp change of the angle. So this fluid particle, let's say we have one more fluid particle here, it cannot go travel like this due to the sharp change. What actually happened, it needs to go like this. So that means what actually happened, it creates some sort of zone here. This is, you can say, kind of stagnation section where the velocity becomes 0 from the both end of the pipe. Yeah. So now you look, due to this 90-degree angle, this fluid particle, it cannot make a smooth turn, so it needs to go like this way. So that means now there is no flow. No flow, it creates some vortex. So there is no flow in this section, in this section. So what happened here? This pipe and this pipe, physically they are the same diameter, but when it is working, the fluid flow is happening. It is this diameter, it becomes like, this is the actual flow diameter. It is called this vena contracta. Like the flow, the surface area, it becomes narrow. So it acts like a kind of a contraction. The pipe becomes narrow. So you see now you can remember the Bernoulli principle, and if you know the mass conservation principle, what actually happened for mass conservation principle. So according to the equation of continuity and the mass conservation principle, the flow coming through the inlet and the outlet, it should be same. So the fluid velocity, it will be maximum here. Due to this reason, you see the less fluid flow surface area, we will get higher loss, and the loss coefficient, that's significant here. On the other hand, like when we have this system for a well-rounded shape, it can make some smooth turning, and we have the whole diameter, that's the fluid flow surface area, and that actually minimize the loss coefficient. So when you will design your system, any engineering project or research project, you see how this inlet actually important when you are just talking about the minor losses. And there is some measurement, like how smooth it will be. We'll discuss it later on. You see here, this from this restriction, this, if we say from here to here, if it is R, so this ratio of this R and this D, for this case it is greater than 0.02 here. But in this case, it makes, it's kind of a sharp 90-degree angles. So I will show you how this turning, this smoothness of this inlet section, how important it is with respect to this loss coefficient. So we have a chart, later on I will show you. So I believe you understand that why it is happening because of this. So the fluid flow surface area, it reduces significantly about this section. So now here, look at this slide. During the exam, you do not need to do anything extraordinary, but you need to use these charts. When this is the inlet, so the flow is going this way. So this is the inlets, all are inlets. You look, in this case, for this pipe inlet, we said this loss coefficient is 0.8 when it is a shower phase, that what I was talking about earlier. So if it is like this, then it is 0.5. But here, it just, I can explain it like this. I need to draw some streamline here. So when this flow is coming, let's say this fluid is coming this way, so it cannot actually go that way. In some cases, it also depends on the speed of the flow. In some cases, it could be like this. So we will see this arrangement and this arrangement. It looks quite similar, but we have the pipe stated from here. That means fluid actually in this section, it cannot go that way. So that increases the overall, the loss coefficient. You see, it's 0.8, but in this case, it is just going this way. So you see, it's relatively lower than that case. And now we discussed this rounded on. Now, when does the pipe exit? So this is for the inlet. So the inlet design, it is really important. I'll show you one chart later on. But when it is the exit, this is the inlet and this is the outlet. So when, let's say this is the pipe coming this way and it is just going up outside through these outlets, it doesn't affect the overall performance. You look here, in all this case, it says the loss coefficient, it is equal to the kinematic correction factor level. This is also the same. This is also the same. The same arrangement for this three. You look, for this different arrangement, we had different loss coefficient. But when we're talking about the pipe exit, it is not affecting the results. Can anyone actually explain why? Because you look, the flow, this is the fluid flow streamline. So when it is coming, it's going straight away. It is not getting any kinds of obstruction here. The same thing happening here. You see, it's just going this way. So this change, it doesn't, make any sense. It will not actually influence the overall performance. The same thing here. It's just going this way. So it doesn't matter actually what is happening here when it is the exit. But when it is the inlet, it matters because the flow is coming all this section, not only from here. It is coming this section as well. I believe you understand, guys. And that's why when it is the pipe exit, we said it is always equal to the kinematic, the correction factor value. And when it is laminar flow, it is equal to the 2. For the turbulent flow, it is equal to 1.05. So if you're solving a problem, a turbulent flow problem, and you have an outlet, okay, so you can simply use it is 1.05. So that you need to take notes. So you will definitely get question in the exam where you need to use the minor loss coefficient. So today I will solve problem where we will have inlet, outlets, we'll have the valves, maybe the bends, okay? So keep notes from this slide. The inlet shape, it matters, but the outlet shape, it doesn't matter for minor loss. And this is the reason why, because the fluid is simply just going out. No shape can change the flow directions. So that's why the minor loss is actually, it's not different for different shapes, outlets. So does that make sense, guys? Do you have anyone got any confusions? Because as I said, like you must need to use this in the final exam. So I believe you should understand it. Will provide more, comprehensive information. You see, I will only actually explain the minor loss today because this is really important. The major loss, the calculation procedure is complex because we need the friction factor. But today I actually, uploaded a spreadsheet in the Teams side, so you can get the spreadsheet like how to calculate the friction factor by using the Excel. So I got one question in the chat. Yeah, we already uploaded every materials, so you can get everything from there. Yeah, so everything I already uploaded. So now you look here. If I say you will get one question from this slide in the final exam, do you believe, guys? So in this slide, we have a lot of information, and you will get the question in the final exam where you must need to use this slide. So we have two things here. Can you tell me what it is? This is the inlet. This is the outlet. Okay. In this case, what we can see, this pipe, it becomes suddenly, it becomes, this. Okay, just a second. All right. So in this case, you can see it is a sudden expansion. This diameter and this diameter. You look, this is small diameter, this is the large diameter. So sudden expansion, and this is the contraction. So initially it was higher, and now it becomes low. You will get a question in the exam where I will provide you the problem, maybe sudden expansion, sudden contraction, or gradual expansion or gradual contraction. So in this case, this is sudden expansion. But you look here, for this problem, it is not sudden expansion. It's gradually expanding. You look here, if I draw the line, you see it's gradually become larger. The same thing happening here. You see it's gradually becomes smaller. So this is important. So do you think this slide contains a lot of information? So this is sudden expansion, gradual expansion. When it is sudden expansion, you can use this chart and you can calculate the heat transfer coefficient, the loss coefficient, minor loss coefficient. How you can do that? It is this one for sudden contractions. Okay, this is for sudden contraction. What do you need? You need to know this diameter D and this diameter D. So for example, let's say this is 2 millimeter, for example, this is 1 millimeter. Or this is, let's say 0.2 millimeter, or this is 0.1 millimeter, for example. So then what will be this D square over D square? Well, you calculate it. It should be 0.04, it should be 0.01, isn't it?
Other way around.
Say again, please.
Shouldn't it be 0.01 over 0.04?
Okay, the small d and the capital. Yeah, that's true. So it's small d over the capital D. Yeah. So what I was trying to tell you is you just calculate this ratio. So let's say, for example, you have this is 0.4, just for example, okay? The 0.4 means you have this is the point. So let's say this. And your loss coefficient should be somewhere here, isn't it? Your loss coefficient should be somewhere here. So what you can do, you can calculate it, and you can do some interpolation. You can get the KL from here if it is sudden contraction. We have got a question, and I will do this. I will use this values, and I will show you how to do all these interpolations. If it is sudden expansion, then it more easier. Like you need to just use this formula, and you can simply calculate the loss coefficient. Now for gradual expansion, it is important. Why it is important? When it is gradual expansion or gradual contraction, it makes, in general, the pipe will be like this. Let's say this is the pipe, but it's gradual expand. So we have an angle here, an angle here, theta. So this is the angle. So when it is the 20 degree, this expansion, that means here 50 degree, 15, this is 15. So for 20, this is 10, this is 10, for example. So when it is for 20 degree, and the ratio of this small d and this capital D is 0.2, the KL loss coefficient is 0.3. For 0.4, loss coefficient is 0.25. So let's say you got a question in the exam where the angle theta is 20 degree, and the ratio of this capital D small d, or small d capital D, this is, let's say, 0.3. So you don't know for the loss coefficient value about 0.3. So you do the interpolation here. So I will show you how to do that. The same thing here for the contractions, we have the data available from the literature for this different angle 30, 45, and 60. Now you can ask me a question that, okay, we have all this information for angle theta equal 20 degree. But what happens if we get a question in the exam, it is 30, 40. So look, we'll not provide you a question in the exam where the data, the information is not available, okay? So do you think this is for the sudden expansion, this is for the sudden contraction, this is for the gradual expansion, this is for the gradual contractions? We are going to use all these informations, and we're going to solve problems in the exam. Okay, so I'm moving to the next slide. Here, you have some more arrangement, because so far what we said, it was the inlet, outlet, and the expansion and the contraction. So now, if we have the bends, so the bend could be sometimes smooth, sometimes like kind of the 90 degree, sometimes you see here. I'm not going to discuss a lot. This slide basically all informations are given. You see different arrangement here, like this is 45 degree. You look here, this is different systems and for different valves. So we have all the informations here. So if you have some problem in the exam where you can see that you have all this arrangement, and you can simply use these expressions. Here you can see some for the gate valve, when it's fully open, then it is 0.2. If you have a gate valve, let's say 1/4 open, half open, just 3/4 is open, closed, sorry, 3/4 is closed, then this is all the the fresh, the minor loss coefficient. And you look here, when it is fully open, it is only 0.2. When it is just the 3/4 is closed, you see it's 17. So the valve, that's the only, we can say we know that a lot of inserts and all those arrangements I said earlier, like the valve, the inlet, outlets, the contraction, expansion, all are responsible for the minor loss. But the valve, gate valve is, we will get the most significant minor loss from the valves. And now you see, if you have a pipe with 3 valves in very short distance and it's almost closed, then you can see how significant will be the minor loss. So it will be then a major loss, and maybe it will be just higher than the pressure loss. So I'm not going to discuss this slide. You have all the information. You can check it later. You can go through this later on. I will just this is we discussed actually earlier. You already know this formula from the previous slide, and we know this this theorem here. It becomes this narrow section. We say this is the vena contracta. The flow becomes highly turbulent in this section and the low pressure in this section. This is the graphical representation. So this figure and this figure are same. Look, this is the contours, the flow contours, and this is some graphical representation of how the pressure head and how the total head is changing. So you look, do you think, guys, in this section, so according to the theorem, the pressure will be higher here, isn't it? And the velocity will be lower at that section. So we know from the theorem that in this section, because this is kind of no flow, this is kind of no flow. So we'll have the high pressure here and the low velocity here, isn't it? So do you agree with me, guys, that in this section we'll have the high pressure and the low velocity?
Yeah.
How about others? So everyone of you just simply agree with me, right? So if you actually, yeah, if you don't want to speak, guys, you can write it down. That's no, it's what I said. It's not correct. In this section, the velocity will be higher because it's now a kind of a narrow pipe. It becomes narrow. It's how the nozzle works. The nozzle outlet, it is very small, so the fluid velocity is significant over there. So in this section, the velocity will be higher and the pressure will be lower, because we know if velocity is higher, pressure is lower, and that you can see here. This is the pressure heads. It is, you see, the pressure is decreased there, but the velocity heads, it's higher. So this is the heads. So this is actually how some graphical presentation. So basically, we discussed why it is happening, because of due to this sharp change of the angle, the fluid cannot just make a smooth turn. We got some sort of this stagnation zone. Do you know stagnation means? Stagnation point means when the velocity is 0. So in this case, nothing is happening. So fluid only going through these sections, and this section is kind of the stagnation area, and the flow area significantly reduces. So all of you should speak with me. This is week 10. Why you people guys feel shy? So you will just participate. You will ask me question. You will answer me. Then I can feel comfortable. Otherwise, I feel like maybe I'm just doing, and you're not enjoying this. It's so boring. So even if you're not enjoying, you should speak. You should just answer the question. Otherwise, it's really hard, because I cannot see you. I cannot see your facial expression. So it's hard to actually continue with this. So yeah, just if I ask something, sometimes I want to confuse you, because I want to see whether you are concentrating or not. This is theoretical thing, but it's very important for real life, because all of you are engineer and fluid mechanics. You must need this concept for different engineering problems. Here, this is, I told you that I will show you a chart, and I'll show you how this rounding, let's say this rounding, like how smoothly you will make your inlet and how it affects the overall loss coefficients. You look here, this is the R, this is the D, R over D, that's ratio. You see, when it is 0, what it means? If 0 means this, that means it is 90-degree angle. Then we found it is 0.5, the maximum. Now, if we make it more smooth, you see, like at this point, you see now when we make more smooth, you see this loss coefficient gradually decreasing. So this gradual rounding of this inlet surface leads this sort of decrease of the loss coefficient. So this is really important when you will design any product. If you work with some related industry, or if you have your own project, you need to design, optimize your system. This is really important. So it is not only the angle, but we need to think about some other thing. Like in some cases, let's say we have the piping system in our kitchen or in our bathrooms. So the space is another issue. Sometimes we cannot make some smooth turn. Let's say you are just driving a car. This is one road, and this is one road, and this is another road. So here is your vehicle. Here is your vehicle. So in this case, you will not get much space to make it turn. But here maybe you have more space. So in real case, we know the theory that, okay, if we make it well-rounded shape, we'll have minor loss. But we'll face some problem in real cases where we have the space limitations. So then you need to think about, okay, you need to come up with some creative design, like how you can optimize this limited space and this design. So then you must need all this understanding. So you will not get everything straightforward in real case. You will find a lot of complicated projects in real life, and then you must need to apply all these theories. So piping system, it doesn't mean that, okay, we know theories, we will do that way. It also related with the cost, the surface area, and and definitely the overall performance of the system. So, and I was talking about one more thing. We'll start with the problem soon. I told you the outlet design doesn't matter. In this figure, it will tell you why the outlet shape, any pipe, outlet shape is not a matter. Actually, what happened here? Let's say this is a lake, and this is a pipe. You adjust, or it is a water reservoir. The flow is coming this way, and the water is just, you are filling the water. So when the water will come, what will happen? It will go directly like this, and then we already have the fluid here. This fluid will mix with this fluid. It will just gain a zero velocity because the fluid is already at rest at this reservoir. So when the fluid will come here, it will not move anymore. So it will gradually become get a zero velocity. That means we'll have all the kinetic energy. That means due to the velocity, it will becomes to the thermal energy. In that case, it will not accelerate the velocity. So what will happen? The velocity will gradually decrease and it will become zero. It will mix with this fluid. So basically, this shape will not affect your minor loss when it is submerged, provided when it is submerged into the any other ambient fluid, water or air, whatever it is. So it will then gain a zero velocity. So this shape, it will not affect the overall the minor loss. And now this is one thing. You see, similarly, so far we were talking about this inlet and the outlets. This inlet outlet. What will happen? This middle like this, the elbows. So you can see when it is making the sharp turn, the loss coefficient is significantly higher than the smooth turn, because this is the same reason fluid can easily just make a turn like this. But here it will be kind of like this. So we'll get some sort of stagnation in these sections. Even we will also when you will do this, then you can see if you search for some saved result, then you can observe the contours where we have the zero velocity over there. So we need to move forward. We say the valve. We usually use the valve. This is one of the most important reason why we get the loss. And what actually happened, I explained, due to this valve or any times of kind of the sharp changes, the flow area, it becomes kind of narrow, and that actually influence the overall performance, and we get the significant minor losses.